All right, so we just talked about how we can graph rational functions when we can use the rules for transformations, but oftentimes the functions aren't written in that form, and so we have to use things like holes, vertical asymptotes, horizontal asymptotes, certain other key features to help us sketch the graph of these rational functions. So let's talk now a little bit about points of discontinuity and end behavior, the first one being what we call holes. A rational function that is not in lowest terms often has a point of discontinuity. Such a point is sometimes called a hole. So what that means is if you take your rational function and you've factored it, if there is a factor in the numerator that can reduce with the factor in the denominator, right? If something can cancel out, what you've just found is a rational function that's not in lowest terms. And that point where the factor that cancels could cause a hole in your graph, okay? Holes are considered what we call removable discontinuity because the discontinuity can be removed by redefining f at that x value, okay? So holes are what we call, again, removable discontinuity. Let's do an example here, an example number 2. We're going to identify any points of removable discontinuity, so any holes. We're going to figure out what the value is of f at that point, and then we're going to figure out where that point of discontinuity is at, okay? So if you look first at part A, it gives us a function x squared minus 4 over x minus 2. Now you might notice, hopefully you notice, that that is not in lowest terms. It's not simplified as much as possible. Because what can we do with that numerator? Right, we can factor it. So hopefully you recognize that this is a difference of squares and you factor the numerator. So take a second and factor the top for me. When you factor, you should have factors of an x minus 2 and an x plus 2. The denominator is already in its most factored form of x minus 2. So now that we have this rational function factored, are there any terms that can reduce, right? Any factors from the numerator and the denominator that are the same? Well, I notice there's an x minus 2 on top and an x minus 2 on bottom. When I cancel those, that tells me that this was not in lowest form originally, and that point is going to cause a hole in our graph. The hole is going to be wherever this makes my function equal 0. So wherever x minus 2 equals 0, that means there is a hole at x equals positive 2. So in this graph, we know that there is going to be a removable discontinuity, a hole at x equals positive 2. Now, when we reduce those factors, we end up with a new function. I'm going to call it g of x, where the remaining piece, the x plus 2, this g of x graph and this f of x graph actually are the same exact picture, just f of x has a hole and g of x does not. If you are a visual person, graph both of those. Graph them and see, probably on any calculator that you use, including Desmos, they look the same exact way because you really can't see the hole because it's so small. But g of x is the same exact graph, just without a hole, where f of x has that hole at x equals 2, okay? The second part of the question says, what is the value of f of x at that point? So if we tried to take x equals 2 and plug it into our original function f, what would happen? So if we plugged in x equals 2, 2 squared is 4, so I have a 4 minus 4 on top. If I plug in a 2 on the denominator, 2 minus 2 on the bottom, 4 minus 4, I get 0 over 0, didn't you? So when you do this, 0 divided by 0 is not 0. It is not undefined. What we call this is indeterminate. So you'll start to see in calculus that when you have a value of 0 over 0, it is an indeterminate value. It doesn't equal 0. It's not undefined like we think. It's not equal to 1. It's what we call an indeterminate form. But anytime when you plug in a value to your function and you get this 0 over 0, what's happening there is a hole in your graph. So we know that this hole is at x equals 2. If we can kind of plug up the hole or use g of x instead because it's the same exact picture, could we figure out where that point of discontinuity is actually at? We know it's at x equals 2, but at what y value is it at? And we can't plug it into f. We already tried that, and we got this indeterminate form, right? So let's actually use g and plug in x equals 2 into the g function. Remember, it's the same exact picture, just without the hole, so we could figure out where the hole is at. If I plug in 2 into the g function, remember g's function is x plus 2, so if I plug in 2, I end up getting 2 plus 2. I end up getting an output or a y value of 4. So what that tells me is that in f of x, there is a hole at x equals 2. The hole is actually at 2, 4. Okay? It is a removable discontinuity at the point 2, 4 in f of x. All right, try the same thing with b. So I suggest you pause the video, try b, and see if you can identify all the points of removable discontinuity, holes. What value do you get when you try to plug that into f? And then what value do you get when you plug it into g? Where is the actual point of discontinuity at? All right, so looking at f, if I try to factor the numerator, I factored it to factors of x plus 5 and x minus 2. I factored the denominator, and I got factors of 3x minus 1 and x plus 5. So you might notice I have a factor on top and bottom, my numerator and denominator, that are the same. So it's not in most simplified form, which causes us to have a hole in our graph. Remember, our hole in our graph is what makes that factor equal to 0. So if I set it equal to 0, I end up getting a hole at x equals negative 5. Now, we can reduce this and come up with a new function that looks the same exact way as our original function, f, just without a hole. Remember, it's the remaining factors that are left over after I get rid of the hole. So can I call them g of x? G of x, which is the function x minus 2 over 3x minus 1, is the same exact picture as f, just without that hole. Okay? Second part of the question says, if we try to plug in negative 5 2x into our original function, into f, what do we end up getting? Take a second, plug negative 5 into your numerator of f, plug negative 5 into your denominator of f, and see what happens. Hopefully, you ended up getting this 0 over 0, this indeterminate form again. Remember, that 0 over 0 means that we have a hole, which is perfect. That's what we were supposed to have at x equals negative 5, right? So how can we figure out where exactly that hole is at? We know it's at x equals negative 5, but let's figure out the y value. Let's use g of x, a similar picture, just without a hole, to figure out the y value when x equals negative 5. If I plug in negative 5 to the x, I end up getting negative 7 in my numerator. I end up getting negative 16 in my denominator. So there is a hole in f at negative 5, 7 over 16. Removable discontinuity.